Hello all. In this video, we are going to discuss about interference. Light was once believed to be as particles, and the wave nature of the light was not accepted. Only after the discovery of this phenomenon of interference, followed by diffraction and polarization, the wave nature of light was accepted. So, interference, on the other hand, has various applications in the technology field, like you can measure the thickness of thin sheets, thin wires using interferometry, as well as the flatness of a surface can be verified. In the discovery of gravitational waves also, laser interferometry plays a vital role. So interference has various applications. So such an topic has to be discussed in this video. Interference. Interference is the phenomenon of superposition of two coherent waves in the region of superposition. So let us consider the waves to be A and B. When these two waves are going to be in phase with each other and they superimpose on each other, they are going to result in an wave C, which is of a greater intensity. This is called constructive interference. When the same waves A and B, they are out of phase and they superimpose on each other, they will result in the minimum intensity, and this is called as destructive interference. So how this minimum and maximum is occurring, or how does this constructive and destructive interference occurring, can be discussed now. Let us say that wave A is going to be lagging than wave B through a distance of lambda, or after one oscillation this waves are going to interfere. In such case also, they are going to constructively interfere, resulting in the maximum intensity. So we can say that when the path difference is any integer times lambda, you are going to attain the maxima, or constructive interference. From that, we are going to calculate phase difference. What is phase difference? It is 2 pi by lambda times the path difference. So substituting in the formula, you will get a phase difference is equal to 2 m pi. Similarly, the condition for maximum can be calculated as when the path difference between these two waves are any odd integer times lambda by 2. So we will get that they are going to destructively interfere and resulting in minimum intensity. So corresponding phase difference is delta is equal to 2m plus 1 pi. Of all the interference applications, you are going to discuss thin film interference in thin film, such as soap film or oil film. How different colors are seen and certain colors are absent. That phenomenon is can be discussed as follows. Let us consider this thin film of refractive index n, and above and below is air of refractive index 1. Ray A, B hits upon this surface and partially reflected along BC, while after B it is going to partially refracted along BD, and at D it is again reflecting along DE, and then from E it is refracted away into air. At D there is an again partial refraction along DI. So there are two rays which are going to constructively or destructively interfere here. A, B is common for the both rays. Third B, BC is the first ray traveling. The second ray is traveling a path of D, D, DE and EF. So there is a path difference between these two rays which are going to be calculated now. Here I and R are angle of incidence and angle of refraction. So path difference can be calculated once we drop the perpendiculars BM and EN here. After this point of N and E, these two waves are of same distance. They have the same traveling distance. So the path difference can be calculated by the formula in the refractive index times the path travel in that medium. So this wave is traveling BD plus DE in the medium of refractive index N. So that is the path travel minus this first ray is traveling only a distance of Bn in air. After n, these two are of same traveling distance. So Bn in air. So n is 1 for air. So 1 times Bn is the path difference between the two reflected rays. We are using this splitting of DE. We can write DE as Dm plus Me. We are splitting that. And using this two triangle, we know that refractive index n is equal to sin I over sin r. Sin I can be written as using this BNE triangle. You can write sin I as Bn by Be, and using this smaller triangle B and E, you can calculate sin R as ME by BE. So BE gets cancelled here, and you'll get BN by ME, and BN is equal to N times B. Here there is a small thing here. You're going to extrapolate this ray, and from this normal is to be extrapolated to be coinciding at G, so that we know what is 2T here. 2T is BG. So BG or GB is 2T here. Path difference, already we have written the same formula here, N times BD plus DM plus ME. From the previous expression, Bn can be replaced by N times Me. That is what has been done here. So N times Me minus N times Me gets cancelled, and we will get the remaining thing here. BD can be replaced by GD. See, BD can be replaced by GD because they are just they are of same angles here. They form isosceles triangle. So BD and GD are going to be the same. So we are replacing that. GD plus DM. GD plus DM is GM. As GM has been calculated as 2R, so we will write 2R. 2R cos R is the left hand side is actually GM is equal to 2T cos R. The path difference can be written as N times GM, so N into 2T cos R, 2NT cos R. We can, by the Stokes theorem, we know that the reflected ray is always suffering a path difference of lambda by 2 due to reflection. So we will include that lambda by 2 here in the path difference. So 2NT cos R is minus lambda by 2 is the net path difference. So this path difference can either be equal to m lambda such that this film will appear bright for certain colors, and we'll substitute for this is the condition for maxima, and we'll solve that and we'll get this. If the condition for darkness is that it has to this path difference must be equal to odd times odd integer times lambda by 2, and we solve that, we'll get the condition for minima. So if my wavelength lambda, say for example, if I have blue color and blue color wavelength of some 400 nanometers obeys this condition for brightness, then you will see this blue color in this air bubble. Or if certain colors are absent here, so those colors are going to obey this condition for minima, and hence they are absent in this thin film. Thank you.